Welcome to the video course on VLSI design. In this lecture, we are going to start with the first topic of module 1 of the course VLSI design. VLSI design is basically a program or professional core course which is offered for the 2022 batch students. The textbook prescribed for this course is with the title of CMOS VLSI design, a circuits and systems perspective. The authors of this textbooks are as follows. The first author and the main author of this textbook is Neil H. Weste, and is a faculty at Macquarie University and the University of Adelaide, Australia. The URL here provided shows the present status of the author and his intention or objective related to the VLSI design has been presented in this video. The second author of the textbook is David Money Harris, and is a faculty at Harvey Mudd College. And the textbook which is presented here, that will cover 90% of the syllabus, which is evident for the prescribed topic. And here there is a supplementary. The authors have provided the supplementary material, VLSI supplementary material, so that students can use this link to download the presentation slides and solution manual for the prescribed textbook. So all those things are available at this following URL. Next, let us move on to the a brief history. That is the first topic of this module 1. A brief history of both transistor and the integrated circuit technology. First, let us start with the evolution of transistor technology and its impact. As we know that in 1958, a name of Jack Kilby by the name at Texas Instruments built the first integrated circuit, which we call as IC, and he built a flip-flop using the two transistors. That was the first invention made by Jack Kilby at Texas Instruments, and this invention has been marked as the beginning of the technological revolution in semiconductor electronics. And here is the photograph of Jack Kilby. It's an old photograph of Jack Kilby, who is holding a lab notebook with the first sketch of an integrated circuit. And this photo was captured in the month of July 1958 at Texas Instruments. And there is another photograph which will show you the right side, which will show you the first working integrated circuit. That is the point contact transistor has been built on the integrated circuit by Jack Kilby. And again, this photograph was captured in 1958 at Texas Instruments. Next, moving on to the next topic is growth in transistor density from 1958 to 2008. Okay, so we are just looking at how exactly the growth of a transistor and growth of integrated circuit has been evolved. By 2008, Intel's Itanium microprocessor, which contains about 2 billion transistors, was released, and this processor also has got 16 GB of flash memory, which was housing over 4 billion transistors. The increase in the transistor count represents a compound annual growth rate, which we call CAGR, of 53% over the span of 50 years. And this is an exponential growth, of course, which is unprecedented in the technological history. Okay, that's about the transistor density. And if you look at the factors that is driving the growth of the transistors, the following are the points to be noted here for the reason for the growth of transistors. The number one is going to be the steady miniaturization of transistors. As we know that day by day transistor size is going to be very less. Shrinking the transistor dimension or size, which will allow the higher density per chip on the chip. That will improve the computational power, of course. More the transistor, the more computational power it is. That is the factor, which is responsible for driving the growth of the transistor. The second important point is advancements in the manufacturing process. As we know that the main manufacturing process is the Taiwan Semiconductor Manufacturing Company, which we shortly call as TSMC. That is the main industry which provides the integrated circuits for the entire world. And of course the other fab houses are there, but the majority of ICs have been fabricated at TSMC. Because of the advancements in the manufacturing process, specifically in the innovations in the lithography process. Litho means it's a single stone, it's a process. And mainly in the innovations in the material science, we know that there are various materials are used in the in the manufacturing of the integrated circuits, specifically the silicon, carbon, arsenic, and plenty of other materials are used. So therefore the innovations in material science also contribute for the contribute for the factor of driving the growth. And also there have been innovations in the chip design, because designers use and manufacturer use variety of the EDA tools for the chip design, and that has been enabled continuously for the growth. And even the scaling is also another important factor. So the scaling factor and scaling elements, those are the couple of factors responsible for the growth of the transistors and hence the integrated circuits. And the third thing is synergistic benefits of miniaturization. What do you mean by this? Unlike the most engineering fields, transistor scaling provides there is significant improvements, okay, in the following parameters, especially in the performance of a transistor. When we scale the transistor, the smaller transistors switch faster compared to the transistor of bigger dimension. The next is going to be the power efficiency. So the transistors which are scaled will have a reduced power dissipation per transistor as compared to the non-scaled transistor. And the cost, lower the production costs, because the scaling of a transistor will make the production cost lower due to the increase in the yield per silicon wafer. So these are the couple of reasons which has been driving the growth of the transistor and hence the integrated circuits. Now let us see the impact of this on the electronics and the society. So the integrated circuit and the transistor has been revolutionized the electronics. So that can be summarized with the following points. The processing power once reserved for government supercomputer is now available for disposable mobile phones. So probably if you can look at olden days where the computer processing power was reserved only for the government supercomputers. Now it's available even for handheld devices as well. The memory once required for a company's entire accounting system is now carried in portable consumer devices like iPods and smartphones. Present day you can see that the 5 GB, 10 GB of the memory we can have it in the smartphones and iPads, which were earlier available only for the accounting systems of public sectors. And the second factor that has created an impact in electronics and society is enabled space exploration and transportation. Probably we all of us know that the SpaceX is doing a significant achievement in the space sector, and probably the evolution or the technology improvement in IC space, integrated circuit space, which played a crucial role in the space missions and improving automobile safety and fuel efficiency as well. So the third point which created an impact on electronics and society is going to be the warfare and connectivity. We already witnessed, how exactly the present war is going on. It's a technology-based war. So therefore, electronics have transformed the modern warfare, which enable the precision-guided weapons and even advanced surveillance. So these are the couple of things which have been improved, okay, because of the electronics. And again, the internet revolution also brought vast knowledge to the web browsers, making global communication easier and even the faster. So these are the couple of things which has been created an impact on electronics and society due to the invention of the transistors and integrated circuits. Now let us see the growth of semiconductor industry. So the semiconductor industry is the second worldwide the leading business compared to the oil business. So let us see how exactly the growth rate impacted the technology. So the market expansion, if you look at, the integrated circuits have become 100 billion per year in the year 1994. That can be witnessed through this graph. Here in this graph, in which we provide year along the x-axis and the global semiconductor billings, okay, in US dollar, in billions of US dollars, that is along the y-axis. So as we can see that this graph is linearly, almost looks like a linearly it is increasing. And if you locate a point at 1994, where in which semiconductor industry witnessed almost $100 billion industry in 1994. By 2007, approximately 6 quintillion, 6 into 10 to the power of 18 transistors were manufactured globally, and nearly it is a billion transistors per person. That is the significant achievement which has happened with reference to the transistor and even the manufacturing. And again, moving on to the next one, you can see that in 2000 we can see that there is again a peak at which we have reached almost, it's a $200 billion. So in this 2000 year, the reason why it has been spiked is because of the Y2K issues, and the people have upgraded the laptops, the computers. Because of those reasons, we have seen a significant spike in the year 2000. And further, there was a dip again here, again because of the complexities and limitations in integrated circuit manufacturing. And further, it has been increased, and the curve continued in a linear manner. And though this was not mentioned till state of the art technology till 2025, probably you can see a little bit of dip during the COVID period, and further the curve has been moving in a linear fashion here. So this is this complete graph shows you the over the year how exactly the semiconductor industry market is moving. And let us look at into the economic opportunities. So thousands of engineers have amazed for fortunes in the semiconductor field. We know that there were plenty of job opportunities created in the semiconductor industry, and even the future opportunities also exist in the basically in the innovative ideas and even technical expertise also. Okay, one was good at the technically, so job opportunities are always open in the semiconductor industry. Now let us look at a little bit of history related to the vacuum tubes and that how we move towards the transistors. So evolution of vacuum tubes to transistors. So earlier, before the 1947, the vacuum tubes were ruling the world. As we know that vacuum tubes, the moment we say vacuum tubes, you can imagine just like a incandescent bulbs. Okay, this you can imagine the structure looks like incandescent bulbs. That's how the structure look like for the vacuum tubes. This contains anode, cathode, and grid. Those were the terminals for the vacuum tubes. And these vacuum tubes were very large, of course, and also the expensive, and they were power hungry, and also they were not reliable. Okay, because frequently these vacuum tubes get heated up when we start operating them and when you start using them in the circuits, and that was a huge the problem obstacle to build the circuits. Later in the year 1947, the transistor was invented, and by the famous the scientists the John Bardeen and Walter Brattain built the first working point contact transistor at the Bell Laboratories. Though initially this was considered as a military secrecy, but later this was made publicly. It was introduced in the year 1948, marking the dawn of the transistor era. And so further the integrated circuit was proceeded in 1958. And here you can see the statement given by the Bell Laboratory. I just read out this sentence for you so that you can see the statement released by the Bell Laboratories. We have called it the transistor, TRANSISTOR, because it is a resistor or semiconductor device which can amplify electrical signals as they are transferred through it from input to output terminals. It is, if you will, the electrical equivalent of a vacuum tube amplifier, but there the similarity ceases. It has no vacuum, no filament, no glass tube. It is composed entirely of cold, solid substances. What is the meaning of this? So Bell Laboratory in 1948 made this announcement, and they said that they have invented a transistor, which is nothing but a resistor, and here the signal, the amplifying signal, electrical signal, which will be transferred from input to the output terminal, and signal will be strengthened by doing that. And its electrical equivalent, it doesn't match with the vacuum tube amplifier. The similarity doesn't exist between vacuum tube and transistor. But the transistor doesn't have any vacuum, and there is no filament, and there is no glass tube within that, and completely it is made up of the solid substance. That was the summary of announcement made by Bell Laboratories in 1948. Further, once transistor was invented, and it was a transistor era. Later on in 1958, there was a development of integrated circuits was popular, and all credit should go to the Jack Kilby, who is the inventor of integrated circuit in 1958, and he recognized the potential of miniaturizing multiple transistors onto a single piece of silicon. Considering this idea, he was the first person to build integrated circuit prototype at the Texas Instruments using germanium slice and gold wires. And Kilby later he received the Nobel Prize in Physics in the year 2000 for his breakthrough. And here are a few couple of photographs which invented by Jack Kilby. The first photograph is nothing but a first transistor which was invented by AT&T Bell Laboratories. This is a point contact transistor. As you can see on either side there is a emitter and collector, and the mid you can see there is a point contact, the base terminal, which will act like a control. So this is the point contact, the base terminal, which will act like a control, and this is a point contact you can see on the bottom surface here. And later the second photograph which will highlights about the integrated circuit. It's quite difficult to here to notice the first integrated circuit, which was completely made up of the silk material, and this was the photo captured in 1958 at Texas Instruments. This complete photograph shows the IC which was built at Texas Instruments. Now let us move to the advancements in transistor technology. Later there were significant achievements happened in the transistor technology, especially for the bipolar junction transistor, though it was announced in 1948, and this was developed by Bell Labs, and the transistor was more reliable compared to other devices, like other existing devices like the vacuum tubes, and it was less noisy and more power efficient than the point contact transistors. Okay, that is the improvement over the existing point contact transistors. BJTs require small current at the base terminal, because base terminal will act like a control terminal for the electrons to move from emitter to the collector. To control a large current between the emitter and the collector, the base current will act like a control. However, their present power dissipation limited the number of transistors integrated onto the single chip. So this is a main problem with reference to the transistor. The power dissipation is limited to manufacture in the integrated circuit fashion. Later, the role of BJT was took over by the metal oxide semiconductor field effect transistors. Shortly, we call them as MOSFETs, MOS. Here, MOS stands for the metal oxide semiconductor. This is based on the structure, and the field effect transistor is based on the principle of operation. How exactly the MOSFET works? It is based on the field effect. So that's how the naming has been kept. And this MOSFET was invented in 1960. Though FET concept was pretty old, but MOSFET invention happened in the year 1960. Okay, so MOSFET become dominant due to their ability to draw almost zero control current while idle. This is the significant improvement of MOSFET over BJTs. MOSFET comes in two types here. One is N-channel metal oxide semiconductor field effect transistor, of course, and other one is going to be the P-channel metal oxide semiconductor field effect transistors. Shortly, we call this as NMOS and PMOS. NMOS is also called as N-type, and PMOS is the P-type, P-channel. The majority charge carriers in the PMOS is holes. Here we have holes are the majority charge carriers, whereas in NMOS, the electrons are the majority charge carriers. So the concept of field effects, as I was mentioning, dates back to the Julius Lilienfeld, which was invented in 1925, and Oscar Heal in 1935. So, though the field effect concept was invented way back in 1925 and 1935, but because of the IC invention, this was kept in dark, and later in 1958 onwards, this has got real life, and that's how the MOSFET and CMOS, come into the existence. But early attempts to build them failed due to the material limitation. This was the problem. Due to material limitation, this was kept, in the dark, from 1925 or 1935 till 1958. Now let us see how exactly the CMOS technology raised. Early MOSFET logic gates, which was built in 1963, a couple of people which we want to name it here. Frank Van Laas at Fairchild, he developed the first MOSFET based logic gates, and then these gates are combined NMOS and PMOS transistor, and that gave rise to the complementary metal oxide semiconductor. Shortly we call that as CMOS technology, of course. CMOS gates consumed nanowatts of power, which is of 6 orders of magnitude lesser than the bipolar transistor. So from here itself it is evident that CMOS consumes nanowatts of power, which is much better, 6-fold better than the bipolar junction transistors. Next is going to be the advancements in MOS integrated circuits. Here we used a process called a silicon planar process, which is an easy way to manufacture integrated circuits. It's simplified fabrication process, making MOS transistor cheaper and also more compact. Because of this, the IC fabrication has become made very simple. Early commercial MOS processors used only PMOS transistors. Way back earlier we were using only the PMOS transistor, but again PMOS suffered from poor performance. Okay. So earlier, we have seen that it's due to the poor performance of this technology, the bipolar technology. We moved into the integrated circuits, MOS integrated circuits. Okay. Now, there was a transition from the bipolar technology to the CMOS technology in the year 1980. So here the NMOS gates, which consumes the power during idle, and then replaced with CMOS. CMOS consumes zero idle power, and which is far better than the NMOS and the bipolar transistors. Okay. Now let's move to the Moore's law and the scaling trends. We should appreciate Gordon Moore, which in the year 1965 he was a chairman of Intel, and he observed that number of transistors per chip doubles approximately every 18 months. And this observation is popularly known as Moore's law, which was even held to be true even for decades. And Moore's law has given us a technology migration from various levels. A small scale integration, where you will see less than 10 gates per integrated circuit, and we have a integration of medium scale integration, which up to 1000 gates per IC integrated circuit. There's a large scale integration LSI, which will house 10,000 gates per integrated circuit, and we have very large scale integration, which will house more than the 10,000 gates per integrated circuit. From 1980 onwards, we label as very large scale integration. And we should also look at the scaling, the Dinard scaling. Dinard is a principle related to the scaling has been arrived by a person called Dinard in 1974, which states that as transistors shrink, they become faster, they become more power efficient, and also cheaper to the manufacture. Okay, so these are certain advantages what we have when the transistor dimensions are reduced. Then power challenges post 2004. Because of the clock frequencies which were leveled to the only 3 gigahertz, there is upper limit for the clock frequency. We cannot manufacture a processor beyond 3 gigahertz because of the power limit. Therefore, clock frequencies were leveled to the 3 gigahertz due to the power limitations, power dissipation limitations. And computer performance now scales to the multi-core, because we can't make single processor more than 3 gigahertz. But alternate solution is going to be the moving to the multi-core processors rather than higher clock speeds. That is the alternate method solution what we have. And also leakage currents in tiny transistors contribute to significant power consumptions. That also can be reduced. Okay, that was the main problem, but using sophisticated techniques this can be brought down. And here we show the two photographs. The first one is going to be the Intel 1101 SRAM. This is the SRAM photograph. And followed that we have again this complete is going to be the processor, microprocessor what we call, which is a 4004 microprocessor, which is a 4-bit microprocessor from Intel, and this will do only the 4-bit operations. And this was a photo captured maybe in way back in 1970 or 90 or so. Okay, and next we move on to the a movement in the upgrade in the transistors. So here we see an x-axis with an year and y-axis with the number of transistors, and this is going to be 10 to the power of 9. That is the number of transistors. In 1970 we started with 4004. That was the 4-bit microprocessor, which typically we call that as a calculator. And then 8008, 8080 processor came, 8086, which is a 16-bit microprocessor. Later we have 80286, 386, 486. Then Pentium era started. Pentium 1, 2, 3, 4. Pentium era started, ended up. Then Pentium M, Core to Duo, Core to Quad, and currently we are almost reached a 24 core processor. That is the latest processor what we have, that was released by Intel. Okay, Intel is the leading in the processor manufacturing. So therefore that was the latest processor manufactured by Intel. In the next graph, we will show you how exactly the clock speed, the increased over the year. And again, 1970, as we can see that the clock speed was just 1 megahertz, and you can see the significant achievement. We reached up to almost roughly it is 3000 megahertz, or we can call this as 3 gigahertz. That was the clock frequency. And as I mentioned earlier, this has got a power limit. We can't increase a single processor beyond the 3 gigahertz due to the power limit. From 2005 onwards, the clock frequency has become stagnant. Instead of having single processor with higher clock frequency, a better solution is going to be using the multiple cores. Next, let us see the advances in the manufacturing and feature sizes. Feature size is very important because that decides the technology. Feature size refers to the smallest dimension of a transistor that can be reliably built. That will decide the size of a transistor. And example is Intel 4004, which was released in 1971. Feature size is going to be 10 micrometer. Intel Core to Duo processor that was released in 2008. The feature size was 45 nanometer. And new technology nodes are also introduced every roughly it is 2 to 3 years, which reduces the feature sizes by 30%. And feature size include micron scale, which is micrometer, which we call 10 to the power of -6, 0.25 micrometer and above. Nanometer scale is again 10 to the power of -9, which is below 250 nanometer. That is the feature size. There are a couple of challenges in the nanometer scale, the processes, because of transistor leakage current increases enormously, and there was a variability in the characteristics of adjacent transistors that will influence the transistors, and there is a resistance wire has been increased like anything. These are the couple of reasons, the challenges that the designers normally face in nanometer scale. And here is a graph of the again year versus feature size, which is along the y-axis. We have started in 1970 with 10 micrometer, and then later 6 micrometer, and presently in roughly it is 13. We have 22 nanometer, and further we'll have the 5 nanometer, 2 nanometer. That's how the feature size will decrease. Miniaturization will happen that leads to the decrease in the feature size. And lastly, we have the future of Moore's law, and also we have made a couple of statements related to the Moore's law. Moore's law has been self-fulfilling prophecy due to the market competition. It has become almost like a stagnant because of the increased in complexity, and there's a tough market competition. And second thing is scaling as fundamental limits. There's again advantages and disadvantages with reference to the reducing the transistor dimensions. Transistor cannot be made smaller than the atom, so that point should be kept in mind. So we can't go lesser than the atom size. Okay, so we have a limit for that. And also we should keep in mind that Dennard scaling has been slowed, and also Dennard has proved in 1974 he has showed performance improvement due to the scaling. And there's again trade-offs are required between the power, efficiency, and the delay also. These are three important constraints when we make integrated circuits. Although per transistor costs have been decreased, today the cost of a transistor per transistor is nothing. It has been reduced like few pi. Okay, but the design costs have been increased exponentially. That is again a challenge. And then state-of-the-art processes are reserved for high volume products. Today, if you go for small volume, maybe the 10 size, 10 ICs, 10 ICs in number, or 20 ICs, generally it costs you very high. So basically, the high volume products will make you the cheaper ICs, and high performance applications especially. And many predictions about scaling limits have been wrong in the past, and because of innovation still continues. And as of 2009, it is believed that Moore's law would persist for another decade. And also with further breakthroughs likely in materials and quantum computing, Moore's law will hold good even for next decade as well. So with that, we have covered a brief history about the transistor and the integrated circuits. In the next class, we will talk about the MOS transistor theory and more details on that. Thank you for watching.